Hi, my name is Aikya, and I'm a Columbia University data science grad student. And today I'm going to present my work on detecting cancer metastasis on gigapixel pathology images. Um, this is part of a course project and for applied deep learning. So, let's get started. So, to give you an overview about the problem here, metastasis detection is typically performed by pathologists by going through hundreds, thousands of slide images from the lab. And this process is very labor intensive and error prone since pathologists have to go through them manually through the slide images. And the objective here is to implement a framework, a CNN architecture to aid the current manual process by improving the speed and also act as a second opinion for the existing metastasis detection. So first, I'm going to go through the methodology I used to extract the patches from the slide images I had from the data. So first, we go through the region of interest from the image slide using thresholding on RGB space. And then we extract the tumor image uh, region from the given corresponding mask image, and then we extract the non-tumor image region from the difference between the region of interest and the tumor regions. We then extract negative samples using coordinates from non-tumor region, and then sample 1,000 patches randomly, uh, each using tumor pixel and non-tumor pixel coordinates. And so we finally get 1,000 from tumor region and 1,000 patches from non-tumor region, and we then label them zeros and ones according to the class they come from. So this is the methodology I use to extract the patches. Moving on, so I used four complete slide images at level 5 to get my patches for the training data. Then I used one slide image for validation and one slide image for testing. All of these patches have been extracted from the image on level 5. Uh, Moving on to the model architecture that I used, so I tried to. Uh, I first started off with VGG, um, but it didn't give me very good results. So I also tried Inception V3, which performed better than VGG. Um, so using Inception V3 model as the base model, which is the same as given in the paper. Um, I link the paper in the description below that I referred for this project. So using the paper on a baseline model, I got a 50% validation accuracy, uh, and then I refined the model by adding a convolution layer to the base model output. That is, for the base model Inception V3 output, I added a convolution layer and then a dense layer with sigmoid activation to get the probabilities on for the tumor detection, and this increased the accuracy to 65%. Um, then I'm further tuning the hyperparameters, lowering the learning rate for the optimizer, improved the validation accuracy to 78%, and adding early stopping with the patients of 3 that increase the validation accuracy to 80%. These are the results. On the left, I have the accuracies, validation and train accuracies from Inception v3 for 30 epochs, and on the right, I have the same for 20 epochs, but for VGG 19. And as you can see, the accuracy is much better for the Inception v3 than VGG. So I finalized on Inception v3 for my predictions. There are a few additions that I thought of, but I didn't implement it over here. Uh, so first is data augmentation. Um, I could have used images in uh, different horizontal flips and created a larger data set, um, and again check the model performance with the improved data set. um, Similarly, the next step would be using images from different zoom levels and increasing the data set for the training. um, Then at the end, I generated a heat map using the model's output to compare uh, to check the model's prediction of where the tumor was on the original slide image. I use larger patches here, but by using smaller patches or training the model to predict the heat map itself, I could have got a more accurate prediction of where the tumor was present visually. um, then also, I didn't train the base model layers in the Inception v3, but maybe training a few layers of the pre-trained model um, would have yielded better results. And the last addition that I propose here is using a larger batch size and greater number of epochs for better convergence. So let me now take you to the code for this project I've been explaining so far. Let's quickly go through the components. Um, this is a code for installing the libraries, and this is for importing the libraries on Colab. Um, readSlide is a function to read the TIF images from the given data. Uh, Find tissue pixels and apply mask are two inbuilt functions to get the region of interest area uh, by segmenting on the RGB space. Com matrix and records are two functions that I've written to generate uh, random patches from the images. Uh, and this random sample is a helper function to perform sampling patches. Uh, Here I have written code to build a cache since the images are huge, and to perform training better. I've cached the images so that it's faster to execute. Um, so build cache is the function for that, and this is just I'm just displaying the images and the corresponding tumor mass uh, that I'll be using for my project here. Uh, yeah, and here I have used the Keras data generator to uh, iterate through the samples uh, to produce the samples in batches of 32 here, and give it to the model fit generator. Uh, Moving on to the model, I've used a base model here, Inception v3, and I've added a flatten at the base model output, and then two dense layers, and finally dense layer with softmax activation. um, yeah, and here is the model summary. Mm, and once I compile and then use model.with generator, here are the POC results, and I've plotted these results, as you can see here. So the green indicates validation accuracy, and I'm sorry, the green indicates the train accuracy, and the blue indicates the validation accuracy. So we get an validation accuracy of about 80 80%. And I've also experimented using VGG19 uh, and plotting these results. Um I get a validation accuracy of about 60%, which is less than the Inception V3 model, and hence I'm going to continue using Inception V3 for my predictions as well. So, this is a test image I used to uh, get my model prediction. So this is my slide image, and on the right I have my tumor mask, and I run my model prediction, and as you can see here, the red indicates tumor detected areas, and the blue is non-tumor pixels. So um, as you can see, the model has detected areas where the tumor was present originally in the tumor mask. So um, I conclude by saying that our approach is a good validation for tumor detection, and as we discussed, this was our objective of the project, uh, to build a framework to detect tumors in slide images, and this could be a very good uh, second opinion for the pathologist to refer to, and this is a good computer supported approach. Um, Thank you.